Great pleasure to be here today with lots of friends. The first time visiting Eurecom, and I hope it won't be the last. And it's been great to be here. So I'm going to talk in the next 15 minutes about maybe a few too many things. This is joint work with a lot of people at Northeastern, and it's been really a pleasure to work on all of these aspects. And we're going to talk about Open6G. Open6G is what we refer to as a industry, university, government R&D center, looking at developing the next generation of open, programmable, virtualized, and intelligent beyond 5G networks. We're looking at developing architectures, end-to-end software stacks, testbeds, as well as algorithmic foundations for next-gen networks that are automatically deployed and controlled through artificial intelligence and machine learning algorithms, with specific emphasis on security, energy efficiency, and spectrum sharing. Now, what we refer to as the technical architecture of Open6G, which is referred to in this chart, is heavily based on the OpenAirInterface Software Alliance protocol stack. We're looking at the component that we call run in a box is a disaggregated version of OAI, and Florian has been working quite heavily on that and helping us with this, and Rajiv, I don't know if Rajiv is in this room. Rajiv, hi, great to see you. And a lot of other people working on this. Core network is also based on OAI. We're also using Open5GS. And we've also integrated the RAN with what we refer to as the Open RAN GIM framework. Open RAN GIM is a set of tools that include the near real-time RIC, non-real-time RIC, as well as a number of scripts and pipelines that can be used to generate data sets, use the data sets to train machine learning models, embed the machine learning models into X apps and R apps, and deploy them in the field. And then there's a number of testbeds that are part of this framework. Colosseum, I'm going to be talking about Colosseum in a minute, as well as testbeds over the air like Arena and X5G, and then the various platforms in the Platforms for Advanced Wireless Research set of testbeds that Hongwei is going to be talking about quite extensively later. So Open RAN is certainly an enabler for AI-based cellular systems. We're looking at a number of problems that can be categorized as problems related with classification, right? Extracting information at different levels of abstraction from the radio access network, using information for forecasting, for predicting traffic loads, the need for mobility, etc., and a number of control problems that span all the different layers of the protocol stack. If you look at specifically the ORAN architecture, disaggregated ORAN architecture you see on the right, I'm sure most people in this room are familiar with the concept of near real-time RIC and non-real-time RIC, and how you can run third-party control applications at different time scales. So there's R apps that look at the time scales that are greater than 1 second, so longer time scales, minutes, hours, etc., and control things like long-term policies, end-to-end slicing, etc. X apps are designed to run on the near real-time RIC with time scales that span tens of milliseconds to hundreds of milliseconds, up to 1 second, and control functionalities that have to do with management of the radio access network, like load balancing, selection of scheduling policies, etc. There's also a notion of DApps. DApps is something that is not standardized by the ORAN Alliance today. It's something that has been proposed by our group as part of the ORAN Next Generation Research Group. There's been a study item that has been going on for the last few months. DApps are distributed applications that run directly on the distributed unit or on the radio unit that interact with low-level functionalities that require authentic real-time time scales in terms of closing the loop between observing information in the run and injecting control actions. And we're looking at timescales less than tens of milliseconds, including authentic real-time, less than 1 millisecond timescales, where you have direct interaction with the IQ samples on the radio access network. We think that we're working in general on a roadmap to enable next generation network control in the radio access network, and we think that there's a lot of need for research activities that span testbeds and data sets. We've had some glimpses of that in today's great talks. And orchestration and automation, that's an area that is, in my opinion, will become increasingly important in the next few years. Conflict management, obviously, we can't really hope that injecting all these different uncoordinated applications at different levels of abstractions coming from different vendors will result in a coherent behavior of the radio access network unless we put in place guardrails for conflict management and coherent orchestration of these functionalities, orchestration of the intelligence, not only orchestration of the functionalities. And last, and I probably won't have time to talk about that, explainability. So the ability to understand a posteriori what is a data-driven machine learning model doing when messing up with a radio access network. So data and testbeds is the first thing that I mentioned. Some here are going to be familiar with Colosseum. Colosseum is it's a large-scale emulator. We refer to it as the Open RAN digital twin these days. It's a data center with a lot of computational power, high-performance computers that are in a one-to-one relationship with software-defined radios. There's 128 software-defined radios, each with 2 front ends. And all of these 256 RF front ends are interconnected through a mesh of FPGAs that is referred to as MCAM, that is able to emulate in real time all the 65,000 channel relationships between the different radios in the system. So we can create rich radio frequency propagation environments over which that are repeatable and over which we can emulate full stack applications and radio access network with hardware in the loop. And so what we do typically is we take a specific RF scenario. Here I'm showing the environment in Rome, Italy. We create a radio frequency model of this environment that we install in the channel emulator. And then we map different software radios to G-Node Bs that are executed in most of the work that we're doing with OAI. And the UEs are mapped to different software radios executed with OAI UE. And this is connected with the software stack that implements the near real-time RIC, non-real-time RIC, and we use a number of pretty powerful GPU nodes to train the models and to do inference in real time in the experiments. We have a tool chain that helps us basically create Colosseum models that reflect different real-world environments, both outdoor environment and indoor environments. And we can do now basically twinning of real-time physical environments in real time. This is a model of Barcelona, and it's executing in Colosseum in real time. So we can move UEs on the virtual map that is reflected in real time in the channel model that is executed to Colosseum, and then we have an execution of a full stack of the of what is happening in the network. Another testbed that we've deployed more recently, and this has been a collaboration with NVIDIA and with OAI, is what we call X5G, which is an ORAN-compliant multi-vendor programmable testbed. We have deployed 8 nodes of this. The radios are based on radio units from Foxconn that are connected with a 7-2 split interface with DU low based on the NVIDIA aerial framework. There is a FAPI interface that has been developed by OAI with NVIDIA, and that connects the CU and DU high components based on OAI with NVIDIA DU low. And then there's an entire framework that is connected with the radio access network that includes, again, near real-time RIC, non-real-time RIC, and it's in a microservices environment based on OpenShift, and provides the ability to deploy all the containers that realize the radio access network basically at the click of a button. And this is just a little bit of the physical footprint of the testbed that spans a couple of different environments. Now, I just wanted to mention the Open Run Gym framework. Open Run Gym is the term that we use for a set of open source tools that help you in the continuum from collecting data at scale on these virtual RF scenarios generated in Colosseum. So there's a set of tools through which in an experiment you can collect data at different levels of abstraction that is necessary for your training, then designing, training, and packaging the IML components as XApps or DApps or RApps, and then testing and refining on these various different platforms that I mentioned. Now, we're doing all of these, as I said at the beginning, to enable next generation network control that needs to be coordinated and organized in a coherent way. At its essence, what we're looking at is what I refer to as the intelligence orchestration problem, right? Where you are given a certain high-level intent, right? For example, I want to serve a certain set of different slices for certain users in a certain city. And then we have a catalog of different machine learning models can be implemented as RApps, XApps, and DApps. And we want to be able to select from this catalog the specific models and the location in the radio access network to execute them to obtain the behavior that we want to achieve. There's a number of challenges related to timing, right? We know that obviously running AI, the inference tasks, takes time. So we need to be able to collect data, so observe the data that comes from the radio access network, execute the models, and then send the output back. So we need to understand whether the AI will be executed in a certain location of the network, will be able to close the loop in the right amount of time. We need to understand where to execute the AI. Is it should be executed in the form of the app close to the radio access network, as an XApps, or as an RApp. Location matters. And number three is understanding conflicts, right? If there's different XApps that are trying to control functionalities that are in conflict, if there's different XApps that are providing contradicting control commands to the radio access network, how should the network which XApp should we prioritize and how bad can it get? So we have also a spin-off that is trying to work on these problems and developing a solution. Something is called the Z-Touch operating system. Spin-off is called Z-Touch, and it's specifically looking at trying to develop a commercial product that can solve some of these problems. In terms of understanding conflicts, we have some recent work that it's available through Archive that is looking specifically at trying to identify the sources of conflicts, model the sources of conflicts using statistical tools, and proposing mitigation policies. We've been able to show, obviously, and I think this is no surprise, I think, for anybody that XApps can result in conflicts that can be detrimental, lead to instability, poor performance, and fluctuations in the performance of the system. We've proposed a way to characterize conflicts between XApps, identifying different kinds of conflicts, direct conflicts where there's two applications that are controlling the same parameters, indirect conflicts where there's two applications that control different but coupled parameters, and implicit conflicts where there's two applications that control different parameters that are, however, coupled through a specific KPM of the network that they affect. And the framework, if you're interested, I invite you to take a look. It's called the Pacifista, the pacifier, and it's really looking at developing profiling mechanisms for the XAPs, conflict detection and conflict evaluation, and proposing conflict mitigation policies. I'm not going to go into any detail, otherwise you're going to be kicked out here, and this has been a collaboration with Deutsche Telekom and Rimedo Labs. Last thing that I wanted to mention is explainability. I think in this framework is another very important issue. We've worked on this in a collaboration with India Networks in Madrid, and we've developed a framework to come up with explanations that link the actions taken by DRL agents into XApps to the network state. So there is basically an ORAN deployment. There is the environment that we are in general observing, a DRL framework that is related to XApps that provide specific control actions. And in this work, specifically, we've been looking at network slicing as a functionality of interest. And then the XAI, the explainability framework, creates graphs that connect actions that are represented as nodes to the effects on the radio access network. And then it creates knowledge by analyzing the transitions between these different actions. And last, there is a component that tries to provide recommendations for improving the behavior based on the explanations that have been developed through this. This is a lot of what I wanted to say, and I don't know if there's time for questions, but if not, I don't know.
First, thank you very much for the presentation. Due to time constraints, we have, for 2 small questions, and then you can, reach Tommaso offline. Is there any question here in the room?
Please.
Thanks, Tommaso, for the presentation. Really interesting. I was wondering whether what is let's say, the most active platform that you are using right now between the Cosmos, the Powder. What is the?
I think in general, I would say that in different ways, all the 4 power platforms are being used quite extensively by several different groups. My group specifically is using primarily Powder today, just because it's a little closer to some of our research needs. But I would say that Cosmos, Era, and AirPow, they all have a pretty significant base of users at this point.
Okay, and you are using it also with industrial partners. I mean, you mentioned NVIDIA, for instance. They are actively contributing to this platform, or they are using.
NVIDIA is primarily working with us at Northeastern on the X5G testbed. That is not necessarily part of Power. Right? It's something that we have developed internally through a different program. I'm not 100% sure if NVIDIA is working with Power platforms, and maybe on Way we'll know more about that. But NVIDIA is working with us at Northeastern directly.
Okay, thanks.
Sure.
Thank you again, Tommaso, for the presentation. So let's move to the next speaker.